Alright, this is an FE review electronics question about a voltmeter. It says a voltmeter is used to measure the voltage across a resistor. You want to measure the voltage across this resistor using voltmeter in parallel with the resistor. So we're putting it in parallel. To obtain an accurate voltage reading, the internal resistance of the voltmeter must be. So the voltmeter has an internal resistance. So if I call this R, if I draw it again, this is our R, and this in parallel, we have our voltmeter. So we want to measure this as accurate as possible. That means this resistance needs to be negligible to this resistance in parallel configuration. So R in parallel with RV is a total equivalent resistor, and you want this to be neglected. In order for this to be happen, it needs to be as big as it can, so almost in infinity, so the equivalent resistance is equal to R. So the answer is much greater than the resistance whose voltage is being measured. So another FE review question about electronics, and this is an analog voltmeter. So assume that you have that voltmeter that has a scale that can move. So the internal resistance of this meter movement is 5 kilo ohm, and the full scale current, in order for it to go that much, it draws 50 microamps of current. So this meter, you want to use it from 0 to 20 volts. What should be the internal series resistor that we need to add so this would be achieved using these values? So our full scale voltage is 20 volts, and the current is 50 microamps. So our full scale resistor, we'll call it our total resistor, is 20 volts divided by 50 microamps, which is 400 kilo ohms. So we have already, so this our total would be Rm plus R series. So this is already 400 kilo ohms, and this is 5 kilo ohms. So R series would be 395 kilo. So the resistance 395 kilo ohm, and it is asking most nearly, so it is most nearly to 400 kilo ohms. So this is about an oscilloscope question, or the function generator question. So the oscilloscope screen has a horizontal width of 10 centimeter, and the height of 8 centimeter. The sweep speed of the oscilloscope is set to 4 milliseconds per centimeter, and the number of cycles, the screen is 4 cycles. What is the frequency of this sine wave? So it is kind of straightforward. So it's 4 milliseconds per centimeter. So it's 4 milliseconds per centimeter. That means this scale here, 4 milliseconds per centimeter times 10 is 40 milliseconds. That means it's from here to here is 40 milliseconds. And in this 40 milliseconds, there are 4 cycles. That means one cycle is 10 milliseconds. So now we know the period, it's 10 milliseconds. The frequency would be 1 over t, which is 1 over 10 milliseconds. That's 100 hertz. and we have it here, B. Another FE review question about semiconductors. So the intrinsic carrier concentration of silicon at room temperature is Ni is equal to 1.18 times 10 to the power of 10 1 over centimeter cube. That means in 1 cubic centimeter there's 1.18 times 10 to the power of 10 intrinsic carriers, and the whole concentration is 3 times 10 to the 2 1 over centimeter cube. It's asking what the concentration of the electrons. So the mass action law says P times N is equal to Ni squared. So the electrons concentration times holes concentration is the square of the intrinsic carrier concentration. So we'll just plug in those numbers. It's equal to 118 times 10 to the 10 square. So then you can find from here electron concentration is 4.6 times 10 to the 17 1 over centimeter cube, which is number D. So another semiconductor question for the FE review. So in metallic materials, electric current occurs due to the movement of electrons. In a semiconductor, so what happens? So in a semiconductor, in most cases in the silicon, you have covalent bonds in between silicon atoms, and when we dope it, what happens is that we either add another electron to the system or we lose an electron. So this electron can move, or this hole can move. So the current can be either with electrons or with holes. Therefore, it's are two types of current flow. One more semiconductor related electricity question in electronics section for FE review. So we have a silicon crystal is 5 mm long and has a rectangular cross section of 20 micrometer to 40 micrometer, and the length is 5 mm. So the donor concentration, so you are given ND donor concentration as 5 times 10 to the 15 centimeter 1 over centimeter cube, and then there's a current that's 2 micrograms, and the mobility is 1.5 times 10 to the 3 centimeter square 1 volt second, and the charge hole of a hole is 1.6 times 10 to the negative 19 coulomb. So we need to find the voltage. So we know the current. If you find the resistor of the silicon crystal, you'll be able to find the voltage. So the resistance is given as the resistivity times length divided by the cross section, or the conductivity times L divided by cross section. So let's find the conductivity. Conductivity is close to the charge times the donor concentration times the mobility, the charge mobility of holes. So if you plug in all those, 1.6 times 10 to the negative 19 coulomb times 5 times 10 to the 15 1 over centimeter cube times 1.5 times 10 to the 3 centimeter square volt second. So if we do that, we will find that it's 1.2 1 over ohm centimeter. So this is our conductivity. Now we can find our R, that is L divided by sigma A conductivity, and here our A is the cross section, which is 20 micrometer times 40 micrometer. If you plug them all in for the R and write V is equal to IR, we would find that voltage would be 0.104 volts, which is closer to 0.1 volt. So the answer would be A. So another FE review question on electronics. This is pertaining to an amplifier or digital circuits. So for t is equal to t is greater than 0 second, the output of an operational amplifier is given with this. And this output is connected to a logic gate that requires a 4.8 volt input to identify its input as a digital 1. What is the approximate time required for the operational amplifier output to reach 4.8 volts? So the equation is given there. So 10 times e to the power of negative t divided by 200 times 10 to the negative 9 seconds. So if you think about it, when t is equal to 0, this equation becomes 10 minus 10 to the e to the power of 0, which is 1. So this is 0. And what will happen is that with an exponential equation, this will look like, and if t goes infinite, this is gonna eventually reach to the 10 volts. So it's gonna go like this. T v of t. So we're wondering when it will reach 4.8 volts, because that's when we can consider it as digital 1. So what we need to do, we just put 2v of t at 4.8 here. It's equal to 10 minus 10v t divided by 209. So put this here, negative 5.2 to the 200 to negative 9. So this is going to become negative 0.52 is equal to e to the power of a negative t divided by 209. So we take the natural logarithm of both sides. We can then it's going to become ln 0.52 is equal to so there was a negative sign, I forgot that, so it's going to be positive. It's going to be negative t divided by 200 times negative 10 to the negative 9, and ln 0.52 is negative 0.65393. So from here t would be 1.308 10 to the negative 7 seconds, which is closer to 130 nanoseconds. Your answer is here.